Do you want to architect for independent systems that you can evolve, scale, and operate individually? Then I have some content for you. Hi, I'm Dirk from the AWS Solutions Architecture team in Germany, and you can enjoy my funny accent today. When it comes to software architecture, I believe two things are really important. One is divide and conquer, the other one is loose coupling. When you work with microservices, you already apply divide and conquer. And a good way to achieve loose coupling is asynchronous messaging. Now, when we talk with our customers about the communications architecture for their microservices landscape, we often hear that they have REST APIs on their radar, but not necessarily messaging. And we think that messaging can have a number of advantages in certain scenarios to reach exactly the goal that I have mentioned in the beginning. Independent systems that you can evolve, scale, and operate individually. That's why this talk is about integration patterns that are based on messaging. Now, when you have seen that the title of this talk and the session catalog, you might have thought, wait a minute, why is this restricted to messaging? Shouldn't these patterns be universal? And you're absolutely right. That's why this talk could also be called Application Integration Patterns not only for microservices, because the patterns are indeed of universal use. But for the reason I mentioned before, I concentrate in my examples on microservices scenarios. Let's have a quick look at the agenda. Subsequently, I will provide a few more words of introduction to further motivate the topic. Then I walk through some fundamental integration patterns that are based on messaging. And to make this more tangible, I brought two example use cases that show how to apply these patterns in real-world scenarios with microservices. In addition, I also show how you can still use synchronous REST API communication between your client and your backend while you use asynchronous communication under the hood. I would like to continue the introduction with an apt quotation from my former colleague Tim Bray. What he says is, if your application is cloud native or large scale or distributed and doesn't include a messaging component, that's probably a bug. And I think that's right. So there's good reason to think about asynchronous messaging, because synchronous systems come with an implication. They are inherently tightly coupled. Think about a request that comes in from somewhere to your microservices landscape. The path that this request takes throughout your services can become complex. And you can quickly imagine that a problem in a downstream dependency can have an immediate impact on upstream callers. And that's why we have mitigation patterns like circuit breaker in the first place. But there are also some trivial reasons to think about asynchronous systems. For instance, some things just take too much time to wait, or they are asynchronous by nature. But now let's proceed with the integration patterns. Patterns are great for architects to talk about things, because they provide a lingua franca so everybody knows what's being talked about. Probably in your everyday work you also use patterns. For instance, the Gang of 4 patterns are a standard pattern catalog in software development. And when it comes to integration, particularly with messaging, there's also a standard catalog. It's called Enterprise Integration Patterns, and it was published in a book with the same title by Gregor Hope and Bobby Wolf. If you have read that book, some of the patterns today will probably look familiar to you. But now let's really proceed with the patterns and start with the basics, message exchange. We can distinguish between one-way and request-response messaging. For one-way messaging, we have a sender, we have a receiver, and we immediately see that the message channel in between can decouple both sides from each other, so they don't have to know anything about them. The sender sends messages into the channel, the receiver receives the messages out of it. For the request-response case, As the name suggests, we have a request and a response, and also then the 2 dedicated channels for each of that. Now, if you think about it, maybe 2 questions rise immediately. The first one is, how does the responder know where to send the response? And the second one is, how does the requester know how to assign an incoming response to a previous request? The first question is addressed by the return address pattern. The requester adds a bit of meta information to the request message that instructs the responder about the address of the return channel. The second question is addressed by the correlation ID pattern. Again, the requester adds some meta information to the request message with a unique ID for the request. And the responder is asked to forward that ID also into the response message. But now let's also understand a bit more about those message channels. We can distinguish between point-to-point and publish-subscribe. Point-to-point is implemented by queues. And we have a sender on the left-hand side that sends messages into those queues. And by the way, there can also be multiple senders, but that's not relevant here. Just for the simplicity in the diagram, I only put 1. And you can have 1 or 0 or a number of receivers on the right-hand side that consume the messages out of the queue. Now, the semantics of a queue is in that way that it acts as sort of load balancer in front of the receivers. That means that every message from the queue is delivered to one of those receivers. That comes with the benefit that it is really easy to scale out your receivers. If the load on the queue becomes a lot, in a way that the receivers cannot cope with the load anymore, you can simply add more receivers to distribute the additional load also on the additional receivers. Another benefit of queues is that they usually can persist the messages. And in that way, it means the messages don't have to be consumed right away, but the queue can, for instance, also flatten a peak load for your receivers. And in that respect, you can also call a queue a buffering load balancer in front of the receivers. And it also comes with another nice side effect that you can safely take your receiver processes offline for maintenance work, and there is no danger that you lose the messages because they are buffered in the queue. How does it look on the right-hand side for publish, subscribe, and topics? Again, we have one process on the left-hand side that submits messages into the topic. It's called a publisher now, and it can be also more than one, of course. And now the behavior is a little bit different because all of the so-called subscribers on the right-hand side will receive, every subscriber will receive every message. In addition, with messaging, topic messages are usually not persisted. That means if one of your subscribers is offline, they will lose all the messages as long as they are offline. Think about it like you run into a forest and shout out loud the answer to the question of life, the universe, and everything, and nobody's with you in the forest to actually receive that nice information. That's really a shame. And there's another thing that we should look at with topics. For queues, we have seen if the load becomes really much, we can scale out the receivers simply. We cannot do that for topics because every subscriber receives every message. That means if we add an additional subscriber, it would see also the message, so that doesn't help here. Let me park that question for a minute and first have a look what AWS servers are in place that actually implement those message channels. Let's begin with the cloud-native ones. We have Amazon SQS, Simple Queue Service for the implementation of queues. And we have Amazon SNS, Simple Notification Service for the implementation of topics. As I said, those are cloud-native and both are serverless. That means there's no infrastructure to manage for you whatsoever. You simply consume the functionality through a simple API. If you're a fan of serverless development, it's also interesting that both services can act as event stores for AWS Lambda. And maybe it's also relevant for you to have strict order on your messages. Both services also support FIFO message ordering. In case that you're restricted to industry standard messaging protocols like JMS or AMQP, there's Amazon MQ, and it's a managed service that can manage on your behalf well-known open source message brokers like Apache ActiveMQ or RabbitMQ. Again, for the serverless developers among you, if you use Amazon MQ with Apache ActiveMQ, it can also act as an event source for AWS Lambda. But you wanted to know how we can make sure that we can somehow scale out our consumer process in the pub/sub message scenario. So there's a simple composite pattern that we can use here, and we can use the two primitives that we have learned about before, topics and queues, and we can simply call it topic queue chaining. How does it look like? So again, we have the publisher process on the left-hand side. It sends messages into a topic. And now we do not directly attach our consumer processes to the topic, but we put a queue in between. And only then we have our consumer processes. And with that, we get the best of both worlds. We can have fan-out functionality, and we have consumer scale-out at the same time, and also the added resiliency, because the message queues can buffer messages for us. So we are also safe to take our consumer processes offline for some maintenance work. I also wanted to show a few message routing patterns and begin with the message filter and the recipient list pattern. Now, the message filter pattern addresses one use case. We have learned that with topics, every subscriber receives every message from the topic. But there are sometimes maybe cases where some of the subscribers are only interested in a certain subset of the messages. In our example here, the subscriber at the top is interested in orange messages. The one at the bottom is interested in purple messages. Now, you could add a dedicated topic for each of those cases, but if you have a lot of permutations, this can quickly become tough to manage. And what helps here is the message filter pattern. So each subscriber can individually agree with the messaging system that it only is interested in a certain subset of the messages. And this is usually done by meta information that is part of each of those messages. And as always, the publisher on the left-hand side stays totally unaware of all this. Now, it's really interesting to compare this to the recipient list pattern, because it's basically the same thing, but it doesn't use messaging. So again, we have a publisher and the subscribers, and there is something in between now that is the recipient list, or implements that recipient list functionality. It manages the subscribers on the right-hand side, and it also manages potential filtering of messages. And since you don't use messaging, that means it's your own code. You can either put it into the publisher directly, or you can have a separate component, as in the diagram here. But it's your own code that you need to manage and maintain. You need additional infrastructure to manage and maintain. And that is something that obviously looks like more exhausting than simply using the message filter pattern. So this is a nice example that really shows the advantages of messaging here. And there's another message routing pattern that I wanted to share with you. It's called the scatter-gather pattern. And it's really a great pattern for use cases where you need to distribute requests across potentially interested or relevant parties, and you need to capture their individual responses. Potential use cases are election or parallel processing scenarios, where you, in the end, search for the best response, or you need to aggregate responses, or maybe both. And it's also, again, a simple composite pattern. We use pub/sub in the beginning. So a requester sends out a request to potential responders. The responders work on their individual response and send it back to a response queue. Again, we can leverage the return address pattern here, so that the responders know the address of the response queue. From there, the individual responses are consumed by an aggregator component, and then finally processed by a processor component. Aggregator and processor can be in the same process, they can be in separate processes. Then again, you can connect them through messaging, and Also, the requester process on the left-hand side can be in the same application as aggregator and processor. And we can leverage, again, the correlation ID pattern here so that we can assign all those responses and the aggregate afterwards to the initial request. With that, we have already enough food, enough patterns that we can use now and apply them to real-world use cases. I have brought two use cases for you, and I want to set the context a little bit. This is Wild Rides. Wild Rides is our favorite fictional technology startup, and they disrupt individual transportation by replacing old-fashioned taxi cabs with unicorns. Because it's much more fun and more magical to ride with unicorns, of course. And they are a modern technology company, as I said. They have a microservices landscape. Probably they implement most of their services in a serverless manner. And I have brought two use cases of them for you, and let's discuss them, how they make use of asynchronous messaging to reach their goals. The first use case is submit a ride completion. Imagine a unicorn has just dropped off a passenger, and now they want to inform Wild Rides about it and also make sure that Wild Rides can collect the fare from the passenger on behalf of the unicorn. So, how does it start? The unicorn picks up the Wild Rides unicorn app. There's probably a button that they can press to send the ride details to the backend of Wild Rides. The app uses the Submit Ride Completion API resource for this, and you can see all the ride details are part of the payload. This API resource is implemented by the Unicorn Management Service in the backend of Wild Rides. And again, I leave out some architecture details here that are not relevant for our discussion. For instance, you can safely assume that there is API gateway in front of the Unicorn Management resource, because we always want to make sure that we separate the actual API from an implementation. Now, what does the Unicorn Management Service do? It probably persists the right details in the database. It creates a new write resource and responds to the client, hey, we have created that resource for you. Here are the details and we are good to go. And again, for our discussion, I have omitted details about the HTTP headers and the right representation. It's not relevant for us, just assume it's in there. Now, as I said, Wild Rides have a whole landscape of microservices, and you can imagine that other services are also interested in that event, that a ride was completed. We have a few examples here. The customer notification service, customer accounting service, there's maybe a customer loyalty service. Of course, there's a data lake ingestion service. Everybody has a data lake today, and so do Wild Rides. And there's one very special service. It's the extraordinary ride service. And that service is only interested in rides that have a fare and a distance across certain threshold values. Now the big question is, how can we integrate this? First option, integration via database. So we have seen in the Unicorn Management Service, there's a database, all the right details are stored there. We could simply share that database with all the services on the right-hand side. What do you think? We could do this, but then we were doing it wrong. Because with that, we would tightly couple all the services on the right-hand side to the specific database schema that we have in the Unicorn Management Service. And as soon as there is a change there, it will most likely break the integration that we have here. And this is a case of tight coupling that I like to call lousy coupling. And we don't want to have that. And I might even want to steal another quotation from somebody, from Roy Fielding this time. And I would say, there's so much coupling on display here that this architecture should be X-rated. So we're not going to do this. What other options do we have? Integration via REST APIs. After all, we have just mentioned Roy Fielding, so that comes to mind. I'm a big fan of REST APIs. They're cool, they make use of the web architecture, and it's an absolutely valid approach here. But it comes at a cost in this scenario. Think about it. The Unicorn Management Service would have to send API requests to all those other services. So it has to be aware of the API endpoints, and we're back to the recipient list pattern. Because you would either have to implement all this functionality into the Unicorn Management Service, or you could also externalize it into a request distribution service, but it keeps the same. There's an additional code and infrastructure for you to manage. Doesn't seem to be like the best and easiest solution here. What other options do we have? Oh, sorry, I should also mention we have still to also cater for the extraordinary write service. So the filter that only the relevant messages or requests are sent to the extraordinary write service here would also have to be implemented ourselves. And again, additional code and infrastructure that we need to manage, while we actually wouldn't want to do it if we don't have to. So there's another option. Maybe it's not the biggest surprise for you now, integration via messaging. What do you think about that? And don't be biased by the fact that the slide already says absolutely, but that's actually the answer. It is the simplest solution here. So we could simply add a write completion topic here. Let's use an SNS topic. It's serverless, there's no infrastructure for us to manage. And all the services on the right-hand side can simply subscribe to it and receive every message when the Unicorn Management Service puts it into that topic. In addition, we can also simply make use of the SNS message filter functionality, something that the extraordinary write service can simply set up with the topic, and then there's no code for us to manage for this either. And if we want to add more resilience here, we can also add a queue in front of every service on the right-hand side, so that we can safely take down the services for maintenance and we will not lose any messages. That was the first use case I brought to you today, and I have a second one. The use case is called Instant Write RFQ, Request for Quotation. Wild Rides are a very progressive company, and so are their customers. So they think it's one thing to simply catch the next available unicorn from around the corner for a ride. And there's another thing that is sometimes maybe much cooler, to ask all the unicorns that are available in vicinity to submit their individual offers. And then they can select the best one for them. And that can be the one with the cheapest price, but it could also be the one that has free additional goodies like drinks on the ride. And this use case is also implemented by Wild Rides. And if you paid attention before, you might have come to the conclusion already that the scatter-gather pattern is the ideal pattern to use here. Let's have a look at the implementation or the architecture. So we have the Wild Rides customer. They use the Wild Rides customer app, type in all their ride details. Well, in particular, it's from where do they want to go and where do they want to end up. And the Wild Rides customer app submits this as a submit instant write RFQ request to the backend. This API resource is implemented by the ride booking service. And again, we spare details like API gateway in front of this. Now, you can imagine that an RFQ apparently takes a bit of time. For Wild Rides, currently there's a default timeout of 5 minutes. And during that time, unicorns have the opportunity to work on their individual offer. And the Wild Rides customer app doesn't want to wait and keeps the channel open all that time. That's why the ride booking service creates a task resource. Obviously, it also stores everything in a database, and we also skip that detail. It creates a task resource and submits it back to the client. So the message to the client is, hey, we have accepted your request, we're working on it. Here is a representation of your running task, and it is running, as you can see currently. And it also comes with a link to refresh that task resource representation. Now, what happens in the back end? The ride booking service publishes this RFQ into the request for quotes topic. On the other side of the topic, we have the Unicorn Management Service, And you can imagine that there are unicorn management resources in there for every active unicorn. But we also want to make sure that we only address the unicorns that are in the area of the customer or where the riot should start. That's why this request for topic is attached to a certain area, and the unicorn management service makes sure that also the unicorn management resources of the unicorns that are in that area are subscribed to that topic. Now, the unicorn management resources notify the unicorns through the unicorn app. That could be done through notifications. And then the unicorns can work on their individual offer, send it back through the app to the unicorn management resource, and those resources then can send it back to the RFQ response queue. Again, we can leverage the return address pattern here so that the unicorn management resources know where to send the response to. And then the write booking service can consume those responses from the RFQ response queue. We have the aggregator and processor component built in. And also the write booking service can leverage the correlation ID pattern here to assign the incoming responses to the previous request. To make the message handling also a bit simpler, the write booking service can use a dedicated RFQ response queue per customer. Okay, now the result of the RFQ is in place in the write booking service, but let's also have a look what the client can do in the meantime. So the client can use, if the customer wants to get an update of the task of the status, it can use the retrieve RFQ status resource and request an update. So as long as the RFQ is running, the status is accordingly. Once the RFQ is done, the status reports it's done, and then it comes also with a link to the result. It can use that link now to retrieve the RFQ result, and now the app can nicely visualize the quotes that came in from the unicorns. That was the second use case I brought for you today. And we are quickly coming to an end now, but I first want to summarize for you what we have heard during this talk so far. So first, I motivated the use of asynchronous messaging for your microservices communications. I then presented a few fundamental integration patterns that are based on messaging. And then to make it more tangible, I brought two use cases that showed how to apply these patterns in real-world scenarios with microservices. If you want to learn more about this, I have a few resources for you. First one is, you can have a look at the AWS blogs on our public website. We have also several ones that deal with messaging and application integration. You can start by searching for those that are tagged with messaging. As I mentioned before, there's also a hands-on workshop that implements actually the patterns and the use cases that I have presented during this talk. And if you feel that an application integration immersion day would help you going forward with implementing your workload in the cloud, please also feel free to address this with your AWS account team. And there's one thing I want you to take away from this talk, and don't forget. Loose coupling is always better than lousy coupling. And with that, I come to an end. I want to thank you for watching today. I really appreciate your interest. If you want to discuss your messaging challenges, please feel free to reach out to me. Oh, and there's one more thing. At AWS, we really value your feedback, and we want to continually improve ourselves. And we think that works best working backwards from customer feedback. So please take a minute and fill out the session survey, and I really appreciate it. Thanks a lot, and goodbye.